to all and welcome to this lecture. We are in module 8, lecture number 1, effective mobility part 2. In this lecture, we will see how we can model our equations based on surface potential and how we can model the current in strong inversion including the effective mobility. These are the learning outcomes of this lecture, which helps you to understand what is the parameters affecting the effective mobility, how effective mobility is actually governing your current equation of the MOSFET. Let us do a quick recap. In previous lecture we said that the mobility in the MOSFET is actually governed by different scattering events, out of which we discussed that phonon scattering, Coulomb scattering and surface roughness. We said that when the field is very low, then the Coulomb scattering is dominated, but when you increase the vertical field, which is denoted by EY effective, right, then the inversion charge come into the surface and they screen this Coulomb scattering, and hence for a particular field this mobility increases, but beyond that value the mobility again decreases because the phonon scattering and the surface roughness scattering dominates, out of which we said that we can define the effective electric field like this. We do have a MOSFET, this is source, this is drain, VD, Vs, and in the surface or in the semiconductor channel we do have inversion charge and depletion charge. So, we define two electric field component, one is Es exactly at the surface and one is E by B exactly below the inversion layer thickness. Simply this is just a simple model we derived as Ey effective is equals to Eys plus Eyb divided by 2. So, we are just averaging out that electric fields. We also derived this equation as Ey effective is equals to minus of Qb dash plus 0.5 times of Qi dash divided by 2 by considering the Gaussian surface and all. We also said that in general we can represent this as Qb dash plus eta E into Qi dash divided by 2, where eta E is dependent on crystal orientations. So, we are going to use these equations today in this lecture. Further, we said that the effective mobility in the MOSFET operation can be given by Mathesian rule, which captures all the scattering event. For example, mu1 is the mobility governed or captured by phonon scattering, mu2 is the mobility captured by Coulomb scattering, and mu3 is the mobility captured by surface roughness. So, at any instant all the mobility effect will come into picture, and we need to include these all mobility effect by mentioning we are deriving an equation for mu effective. By doing some simple math, we calculated that the mu effective can be calculated as 1 over 1 by L 0 to L dx by mu, considering that when the charge will flow between source and drain from 0 to L, then the mobility is also affected along the L, right. That is what the dx term is coming into picture. So, let us move ahead to see can we model this effective mobility with some empirical or semi empirical formula. Let us consider an assumption that we are considering the field is not very low or Ey effective is not very low, meaning you are not in this region, because if the field is very low then Coulomb scattering dominates. So, we are considering that V effective is bit high, where the surface charges are there or inversion charges are there, they screen the Coulomb scattering. In that condition we can simply say the model, a simple model of mobility can be defined as mu is equals to mu naught divided by 1 plus a theta into Ey effective, where mu naught and a theta are constant. They are tuning parameters to get the better fit of these models. In general, this mu naught is half of the bulk mobility, right. The values of mu naught is approximately 400 to 600 centimeter square per volt second for electron and around 100 to 200 centimeter square per volt second for holes. So this is for holes and this is for electrons. The rough value of A theta is around 10 to the power of minus 6 centimeter per volt, correct. Now we will use this equation and fit our previous equation value of Ey effective, which we just mentioned, that Ey effective is can be given by minus of Qb dash, where Qb dash is a bulk charge per unit area and Qi dash is the inversion charge per unit area. So I can fit here and I will get this, which is nothing but mu naught divided by 1 minus A theta by epsilon s, and now you are, or you take at plus, you put minus of Qb dash plus 0.5, or for in general case you take eta Qi dash divided by epsilon s. So that is what epsilon s here is coming. That is what you can rewrite as mu naught 1, this minus will go out, A theta by epsilon s into Qb dash plus eta E into Qi dash. Now we know how we can calculate the effective mobility, as effective mobility is can be calculated as 1 over 1 by L integration 0 to L dx by mu. So I will put this mobility equation or mobility model what I am deriving here to get the effective mobility component. So 1 over 1 by L integration 0 to L dx. Now mu is given by mu naught into mu naught divided by 1 plus A theta Qb dash plus eta E Qi dash, where I have already defined the parameters like A theta, mu naught, Qb dash, Qi dash, any. So this can be solved as, this mu naught will go in the numerator, mu naught divided by, now you need to take an average, in the sense 1 by L integration 0 to L dx plus A theta by epsilon s, sorry I missed a word, a term epsilon s, into integration 1 over L integration 0 to L Qb dash dx plus eta E 1 over L integration 0 to L Qi dash dx. If I rewrite this equation, this will give you 1. So ultimately I can rewrite here, this will give you mu naught divided by 1 plus A theta by epsilon s, and these quantities I can term it as average bulk charge per unit area. So I am denoting it as Qb dash bar plus eta E Qi dash bar, where these are the average charge over the length, right. That is what you are getting here. Sorry, I missed a sign of plus to minus, it will be minus here, because of this minus it will be minus, right. So ultimately mu effective can be given as mu naught divided by 1 minus A theta by epsilon s into Qb dash bar plus Ne or eta E Qi dash bar, where these are the average charge per unit length or along the length. So I can define this as Qb dash is equals to 1 over L 0 to L Qb dash into dx. Now the problem here is, if we go through this model, whatever be the models what we have derived so far, we found that surface potential is a function of x and the charge is the function of surface potential. We haven't encountered any model where the charge is represented in terms of position. So to incorporate or to solve this integral, we need to change the variable. The first variable I need to change to psi s, and then this psi s will related with dx. So that will be a problematic solution or a complex solution. To make it simple, we can simply average out and consider that average bulk charge can be given as Qb dash 0 plus Qbl dash by 2, where Qb 0 dash is nothing but the depletion charge or the bulk charge near source. So we are following same convention what we followed in our previous lectures, like 0 stands for near source and L stands for near drain. Similarly, the inversion charge is given by Qi 0 dash plus Qi 0 L dash divided by 2, where these are the charges near the source and near the drain respectively. Strictly speaking, this averaging out and simplification will only hold good when we consider that the field is not too low. Meaning, if you see the graph again, if the electric field, vertical electric field EY effective is too low or too high, then the Coulomb scattering and the phonon scattering or surface scattering governed, right. That is what, and in these conditions this simplification will not hold. That is what we started our analysis with, an assumption that EY is not too very low. It is a bit high such that the inversion charges are there and they screen itself such that the Coulomb scattering is negligible. Next, we will move further with this and find out what is the value of effective electric field for surface potential based model. As I mentioned, we are actually following QB dash is equals to QB dash bar, or the average QB dash is equals to QB dash 0 plus QB dash L divided by 2. So, we are just averaging the depletion charge per unit along the length, right. Now, we have already seen that QB dash, or sorry, QI dash can be given as minus of COX dash into VGB minus V flat band voltage minus psi s minus QB dash. Now, if I take an average, so I am interested in QI dash bar. This will give you minus COX dash into VGB minus V flat band voltage. Now, I need to take average here. Instead of psi s, I will get what, psi s 0 plus psi s L divided by 2, and this will give you QB dash bar. So, I converted the equation which I derived or we used multiple times in the average inversion charge just by taking the simple form of averaging of the surface potential. Similarly, we have an equation of QB dash which can be given as minus gamma into COX dash square root of psi s. So, if I want an average charge, I can use minus gamma COX dash into square root of psi s 0 plus square root of psi s L divided by 2, right. So, we can use a body reference model and source reference model here. If you see the body reference model, QB dash can be given as this, where psi sm is nothing but what, psi s 0 plus psi s L divided by 2. You remember we have used this term for expansion, right, or expansion point, correct. Similarly, for a source reference model, QB dash is can be given by minus of COX dash into gamma times of psi s 0, because in source reference the expansion point is psi s 0, the source surface potential, plus alpha minus 1 into psi s L minus psi s 0 divided by 2. So, we will use these charge equation, this is 1, this is 2 in our basic equation, where we are actually interested to find out the effective mobility. So, effective mobility was defined as mu naught divided by 1 minus a theta by epsilon s into QB dash plus 0.5 times of QI dash average. Now, where I am considering for the simplicity in this case n eta or eta e is equals to 0.5. So, let us simplify this and then we will put back our derivation or our answer to this equation. Let us define the equation as 1. So, I am rewriting this part only, QB dash plus 0.5 times of QI dash average. It is nothing but QB dash plus 0.5 times of QI dash, which you can take from here, right. So, this will give you minus of COX dash into VGB minus V flat band voltage minus psi s 0 plus psi s L divided by 2 minus QB dash. So, you see here it is QB dash and you will get minus 0.5 QB dash here. So, ultimately you will ended up with 0.5 QB dash minus COX dash into 0.5 into VGB minus V flat band voltage minus psi s 0 plus psi s L divided by 2. So, as we are deriving the equation in terms of terminal voltages, let us solve this, what this parameter and there is another parameter will come as this. So what this value will be? So we are considering the strong inversion case where psi s 0 plus psi s L by 2 can be written as phi naught plus VSB plus phi naught plus VDB divided by 2. This will give you phi naught plus VSB plus VDB divided by 2. This VDB is again can be replaced as what? VDS plus VSB. So if you keep it here, ultimate answer of psi s naught plus psi s L by 2 is phi naught plus VSB plus VDS by 2. This is the value of psi s naught plus psi s L by 2 in terms of terminal voltages. Similarly, what is the value of psi s L minus psi s 0 divided by 2? This is nothing but phi naught plus VDB minus phi naught minus VSB divided by 2, and ultimately this will give you VDB minus VSB divided by 2 will give you what? VDS by 2. So we will keep it here 0.5. Now what is the value of QB dash? The QB dash value you can take this, right? So I am just keeping it as minus COX dash into gamma times of psi s 0. Psi s 0 is what? Phi naught plus VSB, right, plus alpha minus 1 into psi SL minus psi s 0 divided by 2. So ultimately it is VDS divided by 2, we just derived here, right, minus 0.5 COX dash into VGB minus V flat band voltage minus VSB minus phi naught minus VDS divided by 2. That is what we derived here, correct. Let us simplify it. You will get, take minus 0.5 into COX dash common. If you take it out, you will get gamma times square root of phi naught plus VSB plus minus alpha minus 1, no, you will get plus alpha minus 1 into VDS divided by 2, now plus VGB minus V flat band voltage minus VSB minus phi naught minus VDS divided by 2. Now if we see carefully, VGB minus VSB is what? VGS, right. So these term can be replaced as VGS. There is another term we can replace in terms of VT. VT is what? V flat band voltage plus phi naught plus gamma times of square root of phi naught plus VSB. But here we do have negative. So what I will do, I will just add another gamma into phi naught plus VSB and subtract, so that I can take it out and I can make it VT. So this complete equation can be represented as 0.5 COX dash into VGS minus VT, right. So this is VGS, this term, this term, this term, this term, and I am just adding and subtracting gamma into square root of phi naught plus VSB plus gamma into square root of phi naught plus VSB. So this term is captured by this term making VT, and this term plus this term will give you 2 times of gamma into VSB plus phi naught. Now if you solve these two terms, you will get minus 1 minus 0.5 alpha into VDS. Now this is the value of QB average plus 0.5 QI average. I will put back this equation in equation number 1. So putting back the value of QB dash average plus 0.5 QI dash average in equation number 1 will give you this equation. That is the effective mobility equation, where we assumed that a parameter theta is nothing but what? A theta divided by 2 into epsilon into COX dash. You see here 0.5 COX dash is coming up here, this, and A theta by epsilon was there initially, and this minus sign and this minus sign will become positive. So you will get a closed form equation of effective mobility, which is a function of VDS, which is a function of VSB, right, and which is a function of VGS minus VT. So if you see carefully, the important factors which is affecting mu effective is Vgs minus Vt. This is a dominant term. That is what we can simply say the vertical gate voltage, or in general we can say the vertical field affects the mobility. That is what the effective mobility is governed by the vertical field which is provided by the gate, correct. Now we do have a dependence on Vds. If we go for a saturation part, correct, by using the same equation, if I am going to calculate the saturation part of the current equation, which we derived as dIds divided by dVds is equals to 0. We have done this exercise in previous lectures to find out what is Vds dash. Now remember, earlier we considered that mu is constant, but now mu is not constant. Mu is having some dependence on Vds as well. So if you keep this Vds or Vds dependent mu effective in the current equation, you need to do the differentiation of this term as well, and hence the model becomes much more complex. So considering the impact of Vds, the horizontal field is less in the mobility degradation, we can ignore the part of 1 minus 0.5 alpha into Vds. So I will left with mu effective is equals to mu naught divided by 1 plus theta times of Vgs minus Vt plus 2 gamma square root of phi naught plus this is Vsb. Remember, we are actually deriving a equation for a closed form equation for a effective mobility, which helps us to model our current equation and get a good fit with an experimental data. So we need to use this kind of approximation. So the first approximation we consider that we are ignoring the effect of Vds. The second is, if you see carefully, here Vsb term is coming up, which is in the square root. So just to make the model simpler, we are considering a linear effect, and that's what it is derived as mu divided by 1 plus theta into Vgs minus Vt with some parameter theta b, this is Vsb. So again, this is an assumption that we are not considering the complex relation of Vsb with mu effective, we are just considering the simple form. So that will give you this. Here is also a catch. If you see carefully, if you increase Vsb, what will happen to threshold voltage? It will increase. If the threshold voltage will increase there, then this term will decrease, and hence mu effective will increase. So we can simply say if Vsb is increases, effective mobility will increase, right. But if you see physically, then what happens is, this is your source, this is your drain, and this is your body. Increasing Vsb means what? You are applying the voltage like this, right. Increasing Vsb means what? You are increasing the negative voltage at the body, which will create a pushing force of the electron toward the surface. So the electrons which are flowing near the surface will get a pushing force from the back side, and hence they will go near the surface, and hence the mobility should decrease. So this model is also not capturing well about the Vsb effect. So in general, for simplicity, we can ignore this factor also. So overall mobility equation, what we derive is mu naught divided by 1 plus theta into Vgs minus Vt, where theta is equals to a theta divided by 2 into Cox dash into epsilon s. These are well known quantities. I mentioned what is a theta. Cox is the capacitance per unit area. Epsilon s is the semiconductor permittivity, right, which is nothing but 11.7 times of epsilon naught, right. Here it shows that mu effective is dependent on Vgs minus Vt in an inverse relation, right. So if I go further and check the current equation, so current equation in saturation is what? Is approximately equals to Vgs minus Vt whole square, whereas in this term there will be a mobility Cox W divided by L divided by 2 alpha is there. So if this mobility is dependent on 1 over Vgs minus Vt, which is mu naught divided by 1 plus some theta into Vgs minus Vt. So the effective dependence of mu is changes this denominator Vgs minus Vt, and 1 from the Vgs minus Vt from the numerator will cancel out. So Ids is no longer dependence quadratically, with VGS minus VT. So it is almost linear dependence with VGS minus VT due to mobility effects. That we can see from this graph. So what we are doing, we are just plotting the current versus VGS for considering a fixed VSB and very small VDS. So I will help you out why we are considering this case. As I mentioned, the VSB have a complex relation, having a quadratic or square root relation. That is what we have found here, right, and VSB is giving a wrong intuition. In the modeling part, that is what we are keeping a fixed VSB such that mentioning the threshold voltage is not changing while plotting this graph. The second is we are keeping VDS very small, not very small where the Coulomb scattering is dominant, but very small in the sense we need to see the trend from saturation part to linear part, right, or triode region. So you can see this linear curve when you plot the characteristic, so that your the transistor is after threshold voltage, the transistor is entering from saturation to linear. So this is not a very stringent criteria, just to show you that the current will be linear. After this part, the triode region starts. Okay. Now as we see in the triode region, the current is approximately linear to VGS minus VT, correct. It is approximately linear, which can be predicted by this dotted line. However, when you include the mobility effect, then the current is somewhat lesser. So this is a significance of effective mobility which we need to take care of when we are modeling the current equation. Here last I want to mention that at very low field, meaning corresponding to moderate or weak inversion, this model what we had derived is not valid, because we have derived all those equations for the strong inversion region of operation. So let me summarize here. In this lecture we have discussed that how mobility or the effective mobility govern the characteristic of drain current in our MOSFET. We have seen that the effective mobility can be modeled as mu naught divided by 1 plus A theta into Ey effective, where Ey effective is the effective electric field coming from gate, correct. Now we have also seen that mu effective in general is dependent on several voltages, out of which we said that mu divided by 1 plus theta into VGS minus VT plus 2 times of gamma into square root of phi naught plus VSB plus 1 minus 0.5 alpha into VDS. This will be minus. So we do have a dependence of VDS and VSB in the mobility effect model. However, we can ignore these factors considering a good amount of approximation to get a simple model when we model the current equation and including the mu effective, right. So we will stop here for today. Until then, take care.